So, hi, let's get started. The goal of today is to finish this topic so that the next homework will be released after Friday, because Friday you need to submit, I guess it's homework one. I think you have homework 4 that is due on Wednesday, sorry, on Friday. So there will be another homework 5 that cover hypothesis testing, and it will be another homework that cover the last 2 topics. Okay. So let's get started. So, and what do we do today is we will finish the this topic by talking about the last 2 tests we cover, right? Is the compare proportion and compare variance. Okay, so in case after 2 days you forget what we have covered, let me very quickly to go over the what we have done, right? So what we have done for this topic, we have first with one sample test, right? One sample test, right? And for one sample test, we focus on the idea we have a single population, right? And there are potential many data there, right? And this data, we have a summary statistics, right? Which we call the description of what we call mu, right? And sigma square. And in particular, we focus on studying mu, okay? And how we study this, right? And in the hypothesis testing, right, what we say is we have claimed mu equal to certain value called A, right, some value. And what we are trying to do is to test is this claim is supported by the data, right? And how do we execute this idea, right? If the idea is if the data is so the average, the sample average is too far away from A, then we tend to say it's not supporting the claim, right? So the idea is you're trying to get some sample there, right? And some observation, and then you come up with X bar, and how you compare X bar and A, right? Is it far away or not, right? And the idea depends crucially on whether you know sigma square, right? If you know, then it's just a Z.TEST, right? Just X bar minus mu over this one, the Z.TEST, right? If you don't know, then we will have another one, right? If you know this guy, right? If you don't know, then we'll have a T and minus 1, right? T is fine, right? X bar minus mu over S over root n, okay? And this has a distribution Tn minus 1. This has a distribution NCO1, okay? So that is what we have, right? And proportion will be the similar idea, right? What is not written here is proportion pi, you have P, and because proportion imply you know this guy, right? So basically you're using the Z.TEST, right? So that is what we have here. Okay, so the this is the we have covered so far, and then that is we also have what we call the 2 sample test, right? 2 sample test, and what we said is actually instead of single population, we focused on 2 populations, right? Population 1 and population 2, okay? And each populations, right? You have mu, its own mean in its own sigma variance, okay? And what we have said is the first case is focused on whether the independent population, okay, which means that the value here doesn't relate to value there, right? There's no relationship between them, okay? So we are talking about independent. If we have independent population, independent, okay, then we have two cases, right? To see if case one focusing on the H null is asking mu1 is it equal to mu2, right? Asking if the both of them have the same mean or not, holding this is the same, okay? We have assumption, assuming this is true, okay? And we have also have case two, okay, which is also the same, okay, but we have this guy is not equal to, okay. And what is so special about this guy? Because they're the same, okay, we can actually estimate S of P, okay, as pooled variance, right? If you recall, how can we estimate this is N1 minus 1, right? N1 plus N2 minus 2 of S1 square, S2 minus 1, N1 plus N2 minus 2, S2 square, right? So it's a weighted average, right? And then and that imply what is the test statistics, right? Which is T is x bar 1 minus x bar 2, right? Over square root of SP square over N1 SP square over N2, right? This is T N1 plus N2 minus 2, right? So that's what we cover, right? And under this case, right, what the test is, test statistic is x bar 1 minus x bar 2 over the square root of S1 square over N1 S2 square over N2, right? And that's T to the V, and V is given by a very complicated thing, right? But that is what we have said, right? It's independent, right? And we also cover the case where they are pair, okay? And for paired, we actually care about the distance, right? If they're related, right? If they're related, we talk about the difference, right? Each pair is different, right? So we care about a case 3, right? Is talking about H null is asking pi 1 equal to, is mu d is 0, right? What is d? D is just simply say di, it's just x1i minus x2i, right? I is the ith observation there, right? x1i is the ith observation in population 1. x2i is the ith observations in the population 2. Okay, so take a difference. So this is simply you go ahead, just go to a standard T-test, right? So we don't need to worry about that part. Okay, so that is the 2 sample T-test. Okay, so what we are doing today is trying to roughly speaking is going to talk about proportion pi 1 and pi 2. Okay, you say population 1 may be number focusing on girls, how many girls like cats, right? Or they like cat or they hate cats, right? And population 2, we number boys, then ask them whether they like cats or not, right? And that would be the concern if you try to see if you are the seller, you want to see if they're boys and girls, do they have different preference, right? And then you see whether if you're pet store owner, you want to try to sell the cat towards the customer is a If there are sufficiently more women than men like cats, then probably you would try to change your advertising strategy, right? Or sales technique, right? So that is something we want to do. Okay, so that is the first thing we want to do is looking at, again, maybe I use the red color, right? So I have population 1, right? And basically, we talk about binary data, right? The yes or no. So just a bunch of 0 and 1, right? Because 1 means they like, 0 they don't like, so binary data. Okay. So when you say pi 1, right? Just number of 1, right? Over total number of total number, right? How many people they like it, right? The proportion of people who like the cat, suppose we focus on the analog of whether you like the cat, right? So population 2 also a bunch of 1 and 0, right? And 1 he mean like the thing, right? It's just number of 1 again, right? And then total number. Okay. And the hypothesis, what we are talking is whether pi 1 is equal to pi 2, right? Asking if they are same or if they're different, right? So how do you test this, right? The idea is same, right? Because this binary data is just a same as what we have learned in the general case, okay? Just becomes 0 or 1. So what you are going to do, okay, is trying to see the following, okay? And what we are trying to do, maybe I go to the slide because that would be easier when you try to refer to. So what we have, let's go to the so let's go to the slide. Let's slide here. So we start with proportion, right? But proportion, we would say this is the bell curve approximation applies. Okay, the central limit theorem holds more or less. It's like n is big enough, and n times pi 1, and also n times 1 minus pi 1 bigger than 5. So you have a bell curve here. You also have a bell curve there. Okay, and here we rely on the fact that the difference between two bell is also a bell. Okay, and the key thing to calculate here is it is similar to the equal variance under the null hypothesis. Okay, under the null hypothesis, okay, if they have equal proportion, okay, how can you estimate this guy? Okay, turn out to be is very simple. You just don't need to care about the grouping. Okay, you combine the group. Okay, what does that mean? Okay, what does that mean? Go back to here. Okay, here I have, okay, this, remember what you do is you collect a sample, right? You collect some sample, right? You can calculate the sample proportion, right? P1, right? Will be also number of 1 over total number of 1, right? But the fact is within the sample, right? Total number of observation, right? So total number of observation is called N1, right? And this is number of them is X1, right? And similarly, you have the same thing when you collect the sample, we call sample proportion, right? It's number of 1 over total number, right? Sample size, right? So it's just X2 over N2, okay? So, and when we say they are equal to pi, okay, there's some number, right? So obviously, if they're same, how do you estimate pi? Okay, this P1 is an unbiased estimator of pi. Okay. And similarly, this P2 is also an unbiased estimator, right? Because they are both measuring pi. So the question is, you should use P1 or P2 to estimate pi, right? They are both unbiased, right? What we learned is we can use the efficient one, right? So what's the efficient one? Okay, turn out to be, it's just very simple. Okay, the efficient one we call P bar. You just forget about the grouping, just add them up. Okay, and this would be the better estimator, right? Because they're the same, you just group them together, and this is a much better estimate. Okay, then use x1 over n1 or x2 over n2, or any combination would not be better than this one, right? We learned that this is how you do estimation, right? So that is why we have this guy is a better estimate for pi. Okay, and that's why we see this function here. Okay, and once we know this, okay, and this become immediate. Okay, the reason is you can just use the Z.TEST to do the job. Okay, and some of you may, if you are careful enough, would realize that using a bell curve is not entirely correct, right? Because if you are careful, you will notice we do a one sample test. We assume we know what we assume this is a number, right? And that's why we know we have some assumption. That's why we can carry forward. We can use bell curve, right? But here we only say they're the same. Okay, maybe some value, but we did not specify the value. We still have to estimate, right? And you would ask why the bell curve still correct, right? You should imagine that I should use a t, right? And the two reasons, this we don't need to worry too much about it. And first thing, we know if the sample size is big enough, right? Actually, t and the z, the two bell are similar, right? And when you do proportion, it's usually not a big deal. Okay, so that's why we are being lazy here. Just we focus on the normal, will be fine. Okay, this is not very direct. Okay, this is not very direct, but this would be fine when n1, n2 are big enough, and usually when the proportion, usually big enough. Okay, there's not an issue there. So that's why if you try to do proportion, if you just have a small sample size, this may be a problem. But for most applications, it need not be a problem, right? In the business, it's not an issue. But if you're thinking about a medical test where you only have more than several dozens of observations, then you have to think twice whether you need to be a little bit careful. Okay. So I guess let's go to the example, and then probably you will appreciate how we do this kind of problem. Okay, so the Z-test is same as the one sample version. Okay, the only thing I want to highlight is the interval estimator, where you don't use the P bar. The reason is you don't have the H null where they are the same in order to have that, right? Because you are talking about interval estimator. By definition, you are saying that they have the same, that they're different mean, right? So you don't pull it together. Okay, so that is only the technical point that I want to raise here. So I guess it's good to go through this example, and you will see everything that is very similar to what we do for the one sample case. Okay. So the question here, we have a binary data. Okay, we have N1 is 50 and this sample proportion means P1, okay, is 0.6, and we have another N2 is 40, and P2 is 0.7, okay, and the question is trying to ask you is whether that the same proportion or different proportion from two different populations, okay, and let's go to the whiteboard and try to see how what is this question is about. Okay, so let's get started. Is we have the population 1. What we're trying to see is the sample proportion, right? And we assume the normal approximation would work, so this would be pi1, and this would be bell curve. Okay, so this is the starting point we have when we work on this. And the second starting point is we have another, I don't know, another population. We also have the bell curve, okay? And we are not interested in the individual value. Rather, we care whether they're different, okay? In this context now we are working on is we're interested in P1 minus P2, okay? Why we interested in this? Because we care about pi1 minus pi2, right? Because this is, we want to check if the two proportions are the same or not, right? And remember, if the two bell, right? The difference between two bell is still a bell, right? Okay. The difference between two bell is still a bell. And one thing to recall is if, okay, this is a bell for proportion. If we know this guy, we know the variance, right? Because the bell says the variance is like this, right? So this is what we have, right? And we also do the same for the second guy, or this is the variance, right? So if we know pi2, this is the variance, okay? So hypothetically, we would know P1 minus P2, the bell was the variance. The variance just add up together, right? This is what the bell property, right? You take a difference between the two bell, the variance just add up, okay? Because they're independent. As long as they're independent, you can just simply add the variance without any problem. Okay, so that would be the variance. Okay, so under the null hypothesis, right, what we said is we want to see they're the same, so this is equal to 0, right? So basically we're trying to see our null hypothesis is we are in the bell curve. We want the difference about the sample proportion is actually 0, and we're trying to see the data we have is actually 0 or not, right? We do a two-sided test and see if it is in this two extreme area, then we will say the data doesn't support they are the same. Is that clear what we are doing? Again, and then we usually put alpha over 2 here and alpha over 2 there, right? And because we are talking about two-sided one, right? Unless you are talking about it's a one-sided thing, then you put all the alpha on one side, and just same as one sample test, whether you put one side or two sides depend on application, right? So you don't really know what to do. Okay, so and let's see what we have in the problem, right? The problem what we have is, I think we have the problem what we have is, oh sorry, the problem we have is we have 50 and 0.6. Okay, so the problem what we have is how much you have is you have 0.6 here. Okay, I don't know actually 0.6 on the left, on the right, because I don't know pi1. Okay, I just randomly put there. It can be somewhere else. Okay, I don't know whether 0.6 is on the left of pi1 or pi2. I don't know, but just randomly I put it here. And we know n1 is 50, right? I remember correctly. Am I right? Yeah, 50. Okay. Do note that I don't know 0.6 is where. I just randomly put because I don't know pi 1. Okay. And 0.7 can be here. I just okay. But I just try not to confuse you. I put it there. I mean, in case you would want it. It doesn't really matter where you put, right? Because I don't actually know where it is. Okay. So, but if I take these two, okay, take these two, the difference, I do know that from this one, it's actually negative 0.1 is here. Okay. But I don't know whether negative 0.1 here or here. Okay. Which is the case, I don't really know. Okay. Because I don't really know pi 1 and pi 2, right? Because depend on pi 1 and pi 2, right? The bell can be condensed in the center or it's very flattened out, right? Because I have no idea where it is, right? Because I mean, I just fixed the bell, right? But the bell actually I don't know, right? The bell can be very flat or can be not so flat. Okay, is that clear? I mean, I can always draw another bell curve, right? That maybe do you want me to do that? Or maybe I can easier to think in this way, right? Maybe I have 0.1 is here, right? But it's possible that I have another case, right? Which say maybe a color. What color I should use? Maybe this should be the case. Okay. And in that case, alpha for 2 is here. Okay. But I don't know whether which case is true, right? Because I actually don't know the pi 1 and pi 2, right? I don't really know actually whether I have the black case or not. Okay. So what we are trying to do, right, is to consider the case where I transform to Z, right? And 0 is here, right? And I know, okay, when I transform it to Z, okay, how do you do the transformation, right? Under the null, the transformation from here to here, right? It's just any value, right? It's just P1 minus P2, right? Because you minus the mean is here, right? And you over the variance, right? Which is I use the P bar 1 minus P bar, okay, over N1 plus P bar 1 minus P bar over N2, okay. I don't know pi 1 and pi 2, but I can replace it with P bar, okay, which is the best estimate, and I just divide the variance, right, the square root of the variance, and I transform it here, right? So what we want to know is, okay, what is this transformed here, right? And we know that if you look at this area, right, if you try to look at alpha over 2, right, and this is going to be 1.96, right? I think after so many exercises, you know why we have 1.96 here, right? So we try to see if the purple area ends in here or ends in here, okay? So that would be the question, right? Either you can look at the p-value, okay? If it's the case, then it's smaller than alpha over 2, right? And or you can check the other way around. Okay, so that would be the goal. So first we need to calculate the p bar, okay? And then you can transform the negative 0.1, the difference between the proportion, into the Z dimension, right? And then see whether it's bigger than 1.96 or not, or you can check up the p-value, right? Because the critical value is 1.96 for alpha equal to 5%. Okay. So let's actually check it out. Okay. So first thing is to check out the P bar. Okay. And we have 50 people out of 0.6 have like the cat, say for example. And in that case, right, N1 is 50, P1 is 0.6. So how many people actually like the cat, right? Which is 30. Right, people like the cat. And look at N2 is 40 and P2 is 0.7. How many people like cat? Okay, in the population 2, 38, right? So in total, we have 58 people like the cat, and how many people in total? 90. Okay, so that's how you estimate if actually they're the same. Actually, you should have this proportion of people who like cats, right? If you discard the information about two proportion, right? This actually you would discard it if you under the null, right? Under the null, actually there's no difference between two groups, so you can just calculate the proportion, simple proportion as if there's no grouping. Is that clear for the first part? This one okay? So because this holds because the grouping of boys and girls no meaning, right? Just human with a human like cats or not. There's no distinction between boys and girls. Okay, because under null, the same, right? There's no difference. Because proportion, you only need to care about, because the variance, right, the same as the mean, right? So, I mean, it's not same as mean, but variance is given by, if you know the mean, then you know the variance. So, that's the reason. Okay. Once we know this, then we can go to calculate the idea, right? Because this is just P bar, we just calculate, right? This is 1 minus P bar, right? This is N1, this is N2, okay? So basically what it's doing is, this is -1, right? -0.1, and you transform it to the Z space, which become -0.98, okay? So what does that mean? It just mean the purple color in our slide here, okay? Turn out to be, if you transform this guy down here, it's actually much less, it's -0.98, okay? So it's very close, it's here, okay? So even without doing anything, you know actually you're going to not reject the X now, okay? Because this is close to 0 rather than close to the critical value, right? So it's not in the rejection region. So even though without, I mean, further doing the p-value thing, then you're done, right? Just to remind you how you can get this critical value in case you forget. It's just a norm, okay, in the right-hand side, norm S inwards 0.975. This is 5%. Okay. And in case for this guy, right? This is the norm S inward 0.025. Okay. Because 95 in the middle, right? So the two ends are 2.5%. And if you want, you can also calculate p-value here. Okay. The p-value will be the area to the left, right, times 2, because that is the minimum significance level that you will reject the null. Okay, so this will be 2 times, okay, norm as this, okay, -0.98, true. Okay, so that would be the p-value, and you would see without calculation, the p-value would be more than 5%, right? And indeed, actually also more than 10%, right? Which is 1.64. But anyway, so that is what we have. Is that clear why we not reject the X now? Okay. So if you need, I can go back to the slide. Okay. Okay. So because of This is the p-value, okay? And in case you would need an Excel, I can go to Excel, okay? So remember, it should be 2 times, if you look at p-value, right, will be the norm S dot this, okay? Negative 0.98, okay? And true, okay? So this would be the 37%. So the p-value is super big enough, okay? 30%. So you are unable to reject, right? And you also can look at the critical values, which is norm dot S dot inverse 0.025, okay? And this is negative 1.6. And also look at the right-hand side one, which is 97.5, okay? So, but they're symmetry, so you can just use one of them because they're symmetric, okay? So either use one way or the other for your assignment will be fine, right? But only remember when you go to the test, then you only can use the critical value method, right? Because unless you print out a very detailed table, usually you can't really print out the p-value, right? So is that okay? Is there any question about how we do the hypothesis testing? Is that okay? So let's go back to the slide in case it will be helpful. Okay. So that's why we have here we have 1.96, and then that's why this value, right, is there, right? So exactly is what we shown here, right? The value here, the critical value is here, so we don't reject. Or the p-value is this guy. The p-value now is this one, so that's why the p-value is, you multiply by 2, is way, way, way bigger than 5%. Okay, so you really can't reject. Okay. So finally, I want to mention the confidence level. Okay. Although in this context, this estimate is not very meaningful. The reason is being that you can't really reject that different, right? So you can't really reject that same. So that's why this interval is not very meaningful. But nevertheless, I put it there. You still have some uses, okay? So if you try to see, this is the point estimate, right? If they ask, okay, what is different between the proportion of people who like cats between men and women, right? You would say, okay, there's a 10% difference, okay? Sounds a reasonably large number, right? But if you look at the point interval estimate, you will figure out that this value is not very meaningful because it will grow from negative to positive number, which includes 0. Okay, so that means that this is not very informative, right? Because the difference can be less than or can be more than, so it's hard to say, right? And one thing I want to highlight is this guy from here, right? And this guy come from here. Maybe it's use other color, right? And this guy come from here, okay? And do note that for this particular case, this we use their own one, okay? It's not using the common one, okay? Just to highlight this particular point, okay? So that is the you have to be careful about this interval estimation for the proportion difference. Okay, so that is something I want to highlight again, in case you're not aware of that. Okay, if that's okay, then I think I want to focus, or I want to talk about the last test. Okay, before the break. Okay, because this is the last one is called the F-test. Is very simple. Okay, so it can be done in a very quick idea. Okay, F-test. F-test. This is very simple. The idea is the following. We have a population, okay? Population 1. Some data there, okay? And I have a sigma 1 square, okay? This is the variance, okay? And of course, I assume, as always, I assume there's a bell curve applied to the data, okay? And I have population 2, okay? And again, I have some data there. Again, the bell curve up is behind this, okay? And I have the variance here, okay? So I have two bells, okay? And here I don't need to know their mean, okay? What I want to check out is there are two bells. I want to see if they have the same variance, okay? Two bells. I have two bells, okay? I don't care if they're same mean or not, but I want to check out if they have same variance, okay? And how do you proceed this one, okay? This one, we don't go to the math, but actually you can check the slides. But the text is very simple. F, you can just take the ratio of the sample variance. Okay, it's very simple. Just simply take the sample variance. What I meant is you just collect some data here, okay? You calculate its variance. Okay, of course, you collect N1 data there, right? And here you also collect N2 sample here, and then you calculate the sample variance. Okay, you take the ratio, okay, and do the ratio, and then what you do is to check what we call the F table. Okay, but the F table is rather complicated. Okay, and turn out, okay, the F table is not just single dimension like T, right? T, we just have degree of freedom T1, T2 up to Tn. For F, actually the table has a two-dimensional feature. It depends on the sample size of the numerator N1 minus 1 and N2 minus 2, N2 minus 1, okay? So that would be, in this graph looks like. And this F looks like also a complication is it's not symmetric. Looks like this, usually, okay? So what you're going to do is, again, the two-sided test will be looking at alpha over 2 here and alpha over 2 there, okay? And if the same, they will be somewhat nearby here, okay? And you want to check if your data is here, 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 or here and here, right? If they are in the extreme regions, then you reject the null, right? If not, then you don't reject. So the same idea. The only difficulties is two things. First, you have to check the F table, okay, which we'll talk about that soon. And second, it's asymmetric, okay? So you have to check one more value, okay? Check one more value, okay? And let me directly go to the slide and go to example, then you will see how we can proceed, okay? So the critical value is less than the lesser one and bigger than the bigger one, okay? So that would be what we have, okay? So, and the p-value can be a little bit complicated, as later I will show you why the critical value is complicated. Sorry, the p-value is complicated, okay? The p-value is complicated is because in the Z and the T, you know where you are. You can just go to the direction, that's a tail, and then multiply by 2, okay? But for the F, you don't know where the middle point, okay? So that's a little bit more complicated. But anyway, let's see the example. You will see the operation is very simple, okay? So don't worry. This one is actually the easiest test compared in this topic, easiest, okay? So what we have is two population follow the bell, okay? And actually we have a N1 is 50, and we have S1 square, which is 30, okay? And we have another one, which is N2 is 40, and S2 square, which is 20, okay? So we want to see if they have same variance or not, right? The bell curve, just the same idea, two bell, and then see what they say. And as we said, the construction of test statistic is trivial, right? You just take the ratio, okay? And probably you ask why I use 1/2. Actually the same. If you use 2/1, they're the same thing, okay? So it doesn't really matter you put which one, the numerator and denominator, okay? Because if you flip this two will flip, okay? And the same result you get, okay? So there's no particular point whether you put which one is 1, which one is 2. Oh, it's gone. Okay. So that's why you have this S1 square over S2 square, okay? And total to be 1.5, okay? So as we said, this, okay, this guy, okay, this F would have followed distribution of F of 49, 39, okay? So what is 49, 39? Come from 50 minus 1, okay? This 50 minus 1, okay? And you also have this 40 minus 1. Okay, I will tell you what the graph looks like very soon, and this looks like this, okay, in general, okay? So 1.5, I don't know where 1.5, okay? I may know 1.5 if I draw the graph, but without doing this, I don't know whether 1.5 is in here or in here. I don't really know. I don't really know 1.5 is there. But anyway, where's 1.5? It's here or it's here. Okay. But what I want to know is, I want to find out is what is the alpha over 2 here, alpha over 2 there. Okay. And there are two. And first, I want to show you how to Excel first, and then I tell you how to do the F table. Okay. Excel is very simple. Okay. How to figure this out? So we just F this. Okay. Sorry, I want to do the p-value. I want to do the alpha 2, right? Inward, okay, 0.025, okay. And then to tell them which table I'm looking at is 49, 39, okay, and that's it. Okay, and turn out this number is negative 0.0553, which I will show later in Excel. Okay, and for this value, okay, will be the same, will be F inward, okay, 0.975, 49, 39. Okay, so let me check it out. Okay, Excel. So will be equal to F dot inward 0.025, 49, 49. Okay, so that's how I get the 0.335 in the 0.553 in the slides, and also I have F dot inward 0.975, okay, 49, 39 there. Okay, so that's how I get 1.84. Okay, so that means that if I do this, right, this two number, what is the actual case here? The actual thing happening is this guy. Okay, it's not this guy. Okay, it's this guy. 1.5 is here. This 1.84. So it's not inside. Okay, it's not inside. It's outside. Okay, so that means that we don't reject at 5%. Okay, so it's not fall within the region that you think is too far away, right? So it's not too extreme, so it's not something that unexpected, okay? So we don't reject, okay? And the other way to do is what we call the p-value, okay? How can you do the p-value? Actually, it's kind of complicated. As I said, you don't know the left is more or the right is more, right? Because you have to two-tailed test, right? You have to look at the tail area multiplied by 2, right? If you do the wrong side multiplied by 2, you are more than 1, right? More by 2, right? So it must be the case. You have to check out which side is less, okay? So what you're going to do is first you look at the left-hand side. Is it more than 0.5 or less than 0.5? So what we're going to do is we will do the f dot this, okay? And then 1.5, 49, 39, true, okay? So this gives us the left-hand side probability, okay? And as you will see, it turned out it's more than 0.5, okay? So that is an issue with more than 0.5. So that actually is like this diagram, right? It's on the right-hand side. So you have to look at the right-hand side instead. Okay, you have to look. This will be the p-value. Okay, because it's more than 0.5, so you would go. You have to go the other. The tail is on the other hand. It's 1 minus. Okay, so let me actually show how we. Sorry. Where am I? Yes, here. So what I do is I look at the f this, okay, 1.5, okay, and then 39, 49, and then true, okay, and it turns out this is 0.9, so that means that the left hand side is 0.9. That's far away on the right tail, right? It's very close to the tail, so that's why the p-value is you have 2 times 1 minus this guy, okay, so the p-value is close to then 20%, okay, so you still reject, okay, so I think this is already in the slide already. It's the second hand, okay, so it's here, so this everything is done here, okay, so that's why the formula I have is 2 times the minimum of the 2 sides, okay. I guess general question. If no, I guess I end here for the break, and then after the break we'll talk about Excel, how Excel can do everything quickly. So we'll introduce some function here, and we'll talk about it in 10 minutes time. Okay. So I go around to check if you have. I go around to check if any question. Okay. So probably some of you may not aware that there's some typo in the slide which you want to notice. There's typo here. And there's typo. Oh, I forgot this. I forgot to fix this one. This is 6. Okay. So one question is how to test the F table in the exam, right? Because some of you have question how to check. Okay. So to do it is very simple. I just do Google or any search engine you want. Okay. And you type F table. Okay. And I just pick the first one, doesn't really matter which one I use. Okay. So for this one, you can see the F table. Okay. And this is 10%. Okay. So we use 5% as usual. Okay. Then that means that I use this 0.025 for the right hand side. Okay. And that I check 49, 39. Okay. 49 actually we don't have. Okay. Only have 40 and 60 here. So what we'll do is pick the smaller one, use 40. Okay. And 39, you don't have 39, you only pick the 31. So that's why you pick this guy. Okay. So that's how you would do it when you have the F table. Okay. If you ever have to do it. Okay. And that's how that's how you check it out, or this critical value. Okay, so this is the right hand side. Okay. So I guess it'd be good to check out the Excel. Okay, so where we do the Excel can tells you how to quickly do your hypothesis testing. Okay, so the first one is called the Z.TEST, which directly calculate the one sample Z.TEST. Okay, you give them the data, you give them your hypothesis, you give them the population variance, that will give you the answer. Okay, so this refer to here. Okay, this refer to this one. Okay, so here in this question, actually I give you the sample mean, but in reality you start with the sample, right? So maybe to show you the case, I actually do the Excel thing, so you will see what to do. Okay, so let me start with the Excel. Okay, and let me call this hypothesis testing. Okay. So what I'm trying to do is look at the data. Okay, this is data X. Okay, and according to the question, I have 2, 2, 3, 3, 4, 6. Okay. And what I want is to look at the X null, X0, which is what I have is here is 4. Okay. And we do a Z.TEST. Okay, sigma. Sigma is 2. Okay. So these are given by the date. This given the idea, we know what is the mean, right? Okay, so that would be the test we are looking at. Okay, so this is a Z.TEST. So how can we start, right? So we know this one sample test. How can we do Excel? Okay, the first thing to do is to look at the X bar, right? Sample mean, X bar. So bar X bar, right? X bar. What's X bar here? X bar sample mean, so that's why it says average. Okay, so that would be that will be average. Okay, so how can we start? Then we can, this is a one sample test, we know the sigma, so we can have the Z, which is test statistic, right? That comes from X bar minus what the mu proposed, right? And over square root over sigma over square root of how many of them? Okay, which is, let's count, 1, 2, 3, 4, 5, 6. So maybe I just calculate n first. Okay, n is just counting. Okay, just count how many of them. Okay. And then I can replace it by this number. Okay. So this is the Z.TEST, the test statistics, -2. Okay. And then you calculate the p-value, right? What I'm doing here is this is Z is x bar minus mu, right? Sigma over root n, right? Is this. And we know, if you look at, remember this is Z, this is 0, -2 is here. The p-value will be just this guy, right? Okay. And so that's why p-value, if you look at the left tail, okay, the left tail is the green area, right? What you would have is just norm, okay, S, okay. If you are looking at the value to probability, then you will use this, right? And then you use true. Okay. So this is the p-value, okay. And you can also do the p-value is a right tail test, right? Right tail will be 1 minus of this guy because this is the right area. Okay. You can also use the two-tail, okay, p-value. If you do two-tail, okay, how do you do that? Right? Will be, how you do that? Will be 2 times the minimum of the 2, right? Because that is how you should do the p-value, right? Look at the smaller of the both, okay, u times 2. That was the p-value, right? Because you try to look at the standard technical thing, right? It will be just look at the smaller one and multiply by 2, right? Because if you don't know left or right, that's how we do the F, right? If we know that you can just multiply by 2 this one, right? But if you want this to be automatic, this is how you get this one, okay? And this is how you would do one sample Z-test, right? And we can also do the Excel formula called Z-test, okay? That's what we are trying to teach here, okay? We will do Z-test, okay? And you would try to input the data, okay, either A2 up to A7. And what is X is the hypothesis, okay? And you put the sigma there, okay? So oh, sorry. I forgot the square root. Okay, so it should be, I forgot the square root because square root of n. Sorry. So that means that this one actually gives you the right tail, okay? So that this guy is give the right tail, then you can actually calculate the left tail and the two tail easily, okay? So this function tells you if you give the data, how can you do a Z-test quickly? Okay, so this is the first thing. Is that okay? Okay. And and the second one we want to talk about is T.TEST, a 2-sample T.TEST. Okay. T.TEST. And we focus on eco-variance first. Eco-variance. Okay. And let's look at data, okay? And what we are doing is you look at two samples, okay, and see if they are equal or not, okay. So we use T.TEST function, fx2, and we need to tell whether you are one tail or two tail, okay. One means right tail, two means two tail. The last one, two actually means they're equal variance. Three means they are unequal variance. One means they're pair, okay? So this is exactly what we have taught in the class, right? This is case 2, actually case 1. And for our case, this is case 3 is also case 2, okay? So let's see how we are going to handle it. So I'm saying, okay, so this is the question. So this is the data, okay, and this is probably what you do in your project, right? So that's what you have here, okay? And you want to see if the two groups are different, right? So you do a T-test, okay, and you use the equal variance, okay, and how you work it out from scratch, okay. First, you calculate what is x bar 1 or x1 bar, okay, and x2 bar, okay, which is the sample mean of group 1 and group 2. Okay, so you have this or that. Okay, if this is a case, or this is your case. Oh, sorry. Okay, so there are different mean. Okay, and of course, you also want to have how many of them, N1 and N2. Okay, N1, just count how many of those. Okay, of course, you can count it by yourself, but I think it's easier to let the Excel calculate that for you. Okay, and we also want the S1, maybe S1 square, S2 square. Okay, that is just the STDS of the group number 1 and STD EV, okay, for 2. Okay, so this would give us the all the data we need to do the calculation. Right? First thing is you want to calculate the, if you remember the formula, right? We have the test statistic is just x1 bar minus x2 bar over the square root of SP square over N1 plus SP square over N2. Okay, and what's SP square? It's just N1 minus 1 of S1 square, N2 minus 1, S2 square over N1 plus N2 minus 2. Okay, so this is the quick formula we can use. Okay, so we have SP square to pull the variance, which is N1 minus 1 times S1 square plus N2 minus 1 times S2. Okay, so this is the numerator, right? So you have to divide this whole guy by, okay, N1 plus N2 minus 2. Okay, so this would be the formula. Okay, I stop a little bit here because once you've done this, then the T statistic is very simple. Is that okay? This is the SP. Okay, SP square. So you can see the SP square is between this S1 and S2, right? So let's pull the one. Now we calculate the T statistics, right? T statistics. Okay, is what? The numerator it's just a difference between the mean, right? Just 4.5 over 3.5 here. Okay. And you have the square root of, okay, sum of two terms, which is SP over N1 plus SP again over N2. Okay. So this is the formula, right? The numerator is just difference between the mean. The denominator will be just SP over N1 plus S2 over N2, and that's it. Okay. So you can plug in, this is the test statistics. Okay. So if you want to check the p-value, right, you have to use the, because the statistic to the p-value, use the T.TEST, right? Okay. So use the p-value and left. Okay. Okay. How can we do that? Okay. And the p-value, right? You just left hand side, we just T.TEST. Okay. Put this number there. Okay. And the degree of freedom is N1 plus N2 minus 2. So just N1 plus N2 minus 2, right? So this degree of freedom. And then you put true. Okay. So the left hand side is, if you reject on the left, that is 80%. If you try to reject on the right, okay, that will be 1 minus this guy, because the right hand side is just 1 minus the left hand side, right? And if you p-value, if 2 tail, then will be just 2 times the minimum of the 2, right? Because you can just 2 times the right, because in this case, but in general, that's how you calculate, right? This is the general method, because you multiply 2 by the smaller one, right? Because you know where the tail is. Okay. And these are the p-values. Okay. And here I want to use the T.TEST. Okay. This is a function that will prove convenient to do all this quickly. Okay. So we'll try to give you these two values, okay, that you can actually match. Okay. So that's called T.TEST. Okay. And you input this number, and these are the entry. Okay. You input this entry. And then you tell them I'm doing a one tail test, which is right tail, 1. And I'm doing a equal variance, which is 2. Okay. Let's see. If I do something wrong. Let's see the T.TEST. Two-tail one. Let's see. I should have the same result, but why? Sorry, just wait a second. Let me check if there's a issue here. Static variance, right? Oh yeah, it's not static variance. Sorry. Yeah. Okay, so you can see this number are the same as the 2. So you can see the T-test actually can skip many steps if you want to do it quickly. Okay. And just to remind you, some of you actually asked, make sure that you check it again. If you want to use critical value method, right? You can check all the critical value. Okay, the left and the right, right? Suppose I do 2 tail test, right? That's what you do. It will be T dot T inward 0.025. Okay, the degree of freedom will be just N1 plus N2 minus 2. Okay, so this will be the critical value, the left-hand side. And you also have the critical value on the right-hand side. Suppose you do a 2 tail test. Okay, this is assuming a 2 tail test here. Okay, you will be doing the inverse. Okay, so that would be, but that's symmetric anyway. So that you can see the T is between these two critical value. So if you choose 2 tail test, though you don't reject. Is that okay? Okay. So this is equivariance. Okay. So you can also do the unequal variance. Okay. So let me copy this whole thing, and I do the unequal variance. And if you remember, this thing is like you don't need to calculate the PSP. Okay, there's no point of calculating this guy. Okay, but what you need to calculate is a V. Okay, this is the thing that actually distinguish what is the V. Okay, this degree of freedom, and the degree of freedom is a very complicated formula. This formula is like S1 over N1 square plus S2 over N2 square over S1 over N1 square, right? N1 minus 1, N2 minus 1, S2 square, N2 square square. Okay, so it's a rather crazy expression. Okay, so that's why we need to do the calculation. Okay, this is rather complicated. Okay, so the numerator just S1 over N1, okay, square plus S2, okay, plus S2 over N2, okay, square. So this is the numerator part, right? Above, okay. And you need to also enter the denominator. Okay, denominator is rather complicated, but you will do the same. We will do S1 square over N1 square and divided by N1 minus 1. Okay, and add the same thing again, S2 over N2 square over N2 minus 1. Okay, so this crazy thing, okay, I think it's rather crazy. Would okay, that I think that's fine here. Okay, so degree of freedom actually is 4. Okay, it's 3, so you use the lower one. It was 3. Okay, and the test statistics, okay, is not using the pool one, so you would be using D6 and D7 here. Okay, use the S1 S2. Okay, and the degree of freedom, you just use this 3. Okay, this is the only thing that changed here. Okay, the 3 is this is an important thing. Okay, and you want to compare the case to the Excel one, which you just changed the last one from 2 to 3. Okay. And that should give you the formula. Did I do it wrong? Let me check. Yeah, that's right. The formula is correct. Oh, I see. I need to. Okay, I forgot. The formula is. I need to take a square outside again. So I have a wrong memory. So it should be square here, and square there. So I need to change the V. So it should be so it's 7. Yes, so that's right. So you can see the p-value is like exactly what they want, right? So they're the same. Okay, so that's why you can see if you actually know the Excel, things become much easier. All right, so you can quickly go to the answer much faster. Okay, so I guess I will end here. We'll talk about F-test and the remaining Excel, but by now I think you already know how to handle your assignment already. Okay, so the assignment will be released on Friday. So again, you given 2 weeks to do it. So I'll see you next week. Have a nice day.